For nearly a century, scientists thought the edge of the solar system was a solved mystery. Then Voyager got there. What it detected revealed that the boundary protecting our entire cosmic home was farther away, stranger, and far more complex than anyone had imagined. Tonight, you'll discover the shocking discoveries Voyager made at the frontier of the solar system and why they forced humanity to rethink the limits of its own world. Get ready? Let's begin. There was a map. Every American classroom had one. The sun at the center, 8 planets in clean, perfectly spaced rings around it, and at the very edge, a neat outer boundary marking where the solar system ended and empty space began. That map felt complete, settled, final. It was wrong. Not slightly wrong. Not wrong in minor technical details that only specialists care about. Wrong in the way that matters most. Wrong about where the boundary actually sits. Wrong about what shape it holds. Wrong about what lies on the other side. And wrong about what happens when you try to cross it. The map on that classroom wall was a confident drawing of something no human had ever actually visited. And for decades, the scientific community built increasingly sophisticated versions of that same map. More equations, more simulations, more computing power, and grew increasingly certain they had it right. Then 2 spacecraft went there, and everything changed. But before we get to what they found, you need to understand what that boundary actually is, because this is not just a line on a map. This structure, invisible, enormous, and almost never discussed outside of scientific journals, is the reason life survives on Earth. The sun is not quiet. It never stops. Every second of every day, in every direction, it fires a continuous stream of charged particles outward into space. Protons, electrons, plasma so hot that atoms are stripped apart completely. This is the solar wind. It flows at speeds between 250 and 500 kilometers per second, not occasionally, not only during solar storms, but always, without pause. Every hour of every year across the entire 4.5 billion year history of our solar system, the sun bleeds roughly 1 million tons of material into space every single second. That sounds catastrophic. It isn't. The sun is so immense that this loss is essentially meaningless across billions of years. It is a giant that barely notices what it sheds. This solar wind does not travel forever. The space between stars is not a perfect vacuum. The interstellar medium, the thin gas filling the galaxy between star systems, contains roughly 0.1 atoms per cubic centimeter. Hydrogen, helium, trace amounts of heavier elements, almost nothing by any ordinary standard. But our entire solar system is plowing through this medium at roughly 490,000 miles per hour. From the sun's perspective, it is a headwind. A slow, thin, relentless headwind, pressing back against everything the sun sends outward. Where the outward pressure of the solar wind meets the inward pressure of the interstellar medium, those 2 forces find a balance point. The solar wind can push no further, a boundary forms. Scientists call it the heliopause. It is the outer wall of what they call the heliosphere, the vast bubble of solar influence that surrounds every planet, every moon, every comet, every asteroid in our solar neighborhood. Inside the heliosphere, the sun's magnetic field dominates. The sun's particles fill the space. The sun rules. Outside the heliopause, none of that is true. The galaxy takes over, and the heliosphere is not just a scientific curiosity, it is a shield. The galaxy is violent. Supernova explosions, pulsar winds, and other catastrophic events constantly accelerate particles to near light speed galactic cosmic rays, high-energy projectiles that stream through interstellar space in all directions. The heliosphere deflects and weakens a significant fraction of those rays before they reach the inner solar system. Without it, the radiation environment on Earth would be dramatically different. The heliosphere is, in a very real sense, the reason the game of life was ever allowed to start on this planet. So understanding the heliosphere, its size, its shape, its structure, is not an abstract academic exercise. It is one of the most consequential questions in all of planetary science. By the 1980s and 1990s, scientists believed they had the answer. They had built three-dimensional magnetohydrodynamic simulations equations that model magnetized plasma under pressure. Tested and refined over decades, they fed those models with solar wind measurements taken by spacecraft near Earth. They estimated the density and pressure of the interstellar medium using astronomical observations of distant stars and radio emissions from hydrogen clouds. They ran the calculations hundreds of times. The results were consistent. The heliopause, their models predicted, should sit at roughly 90 to 100 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, approximately 93 million miles. So 90 to 100 astronomical units placed the heliopause somewhere between 8.4 and 9.3 billion miles out. The shape, the model said, would be roughly spherical, perhaps gently elongated in the direction opposite the Sun's motion, forming a soft tail, but fundamentally symmetric. A bubble, predictable, clean. And the transition across this boundary, scientists calculated, would be relatively swift, a few weeks, maybe a few months at most. A crossing spacecraft would detect the solar plasma disappearing, galactic cosmic rays jumping to higher levels, and the magnetic field rotating as the Sun's influence gave way to the galaxies. Then it would be over. The spacecraft would be in interstellar space. Case closed. This confidence was not careless. The physicists who built these models were working with the best tools and data available. The magnetohydrodynamic equations had been validated in laboratories and in space. The simulations had been stress tested. The assumptions had been examined from multiple angles. Everything pointed to the same answer: 90 to 100 astronomical units, roughly spherical, a clean transition. There was only one question remaining: who would actually go there and measure it directly? And when 2 small spacecraft finally arrived, what they found looked nothing like any model that had ever been drawn. The year was 1977, and NASA was staring at a window that would not open again for 176 years. 4 planets, Jupiter, Saturn, Uranus, and Neptune, had aligned in a configuration so rare that the last time it happened, the United States did not yet exist. This alignment made something possible that would otherwise be essentially impossible: visiting all 4 outer giants in a single mission, using each planet's gravity to slingshot a spacecraft to the next. No extra fuel needed, no separate missions. 1 launch, 4 destinations, but only if you left at exactly the right moment. NASA called it the Grand Tour, and they built 2 spacecraft to fly it. The technique that made it work is called gravity assist. When a spacecraft flies close to a massive planet, the planet's gravitational field pulls the spacecraft inward and accelerates it, then releases it on the other side at a higher velocity, the same way a baseball thrown from a moving truck travels faster than one thrown from a standstill. The planet loses an infinitesimally tiny fraction of its own orbital energy in the process. The spacecraft gains enormously. No rocket burn required, pure physics, exploited with surgical precision. Voyager 2 lifted off from Cape Canaveral on August 20th, 1977. Voyager 1 followed on September 5th. 1977 launched second, but traveling a faster trajectory, designed to reach Jupiter and Saturn ahead of its twin. The names reflect arrival order, not launch order, a small but persistent source of confusion for anyone who encounters them for the first time. Each spacecraft weighed 1,820 pounds and stood 12 feet tall. Smaller than most SUVs on an American highway, yet packed into that frame was one of the most sophisticated collections of scientific instruments ever assembled for deep space. Cameras, magnetometers, plasma detectors, cosmic ray sensors, infrared and ultraviolet spectrometers, plasma wave receivers. Every instrument chosen to extract maximum scientific value from a planetary flyby lasting only hours. The computers running all of this were, by any modern standard, almost comically primitive. 3 separate processor systems worked in parallel, one handling commands from Earth, one processing science data, one managing the spacecraft's orientation and pointing. Together, their total memory capacity was 68 kilobytes, less than a single photograph taken by a smartphone today. Yet engineers have successfully uploaded new software to these machines multiple times across 5 decades. In 2023, when a corrupted memory chip began scrambling Voyager 1's data, a team of engineers diagnosed the problem from 14 billion miles away and wrote a software patch that rerouted the data around the damaged chip. It worked. 68 kilobytes of 1970s hardware, still accepting code updates in the 21st century. Power comes from 3 radioisotope thermoelectric generators on each spacecraft RTGs. They contain plutonium-238, which decays naturally and produces heat. Thermocouples convert that heat directly into electricity. No solar panels, no batteries in the conventional sense, just the slow, steady, reliable release of energy from radioactive decay. At launch, each spacecraft generated 470 watts less than a standard kitchen microwave. By 2025, Voyager 1 has approximately 249 watts remaining. The decay is relentless and perfectly predictable. About 4 watts lost every year, without exception, without negotiation. Communication happens at the speed of light, and it still takes forever. A signal from Voyager 1, traveling at 186,000 miles per second, requires more than 22 hours to reach Earth. That means sending a command, waiting 22 hours for it to arrive, then waiting another 22 hours for confirmation that it was received. A single back-and-forth exchange takes more than 44 hours. Every instruction must be written with absolute precision, because there is no opportunity to correct a mistake in real time? None whatsoever. The transmission power of each spacecraft is 23 watts weaker than an LED bulb in a living room lamp. By the time that signal crosses 14.8 billion miles of open space and reaches an antenna on Earth, it has spread across an area so vast that the power arriving is roughly 1/quintillionth of a watt. That is a decimal point, followed by 17 zeros before you reach the 1. It is the faintest signal that humans routinely capture and decode from any source in the universe. Capturing it requires the Deep Space Network 3 complexes of massive radio antennas positioned around the planet in Goldstone, California, Madrid, Spain, and Canberra, Australia, spaced evenly enough that as Earth rotates, at least one complex always has a clear line of sight to each Voyager. Each primary antenna spans 230 feet in diameter. Together, they form the most sensitive listening system ever built for communication with human-made objects. And what were these extraordinary machines originally built to do? Visit Jupiter and Saturn, spend 5 years in space, then go quiet. That was the plan. That was the design specification. That was the expected end. No one in 1977 was designing these spacecraft to cross the heliopause, sample the interstellar medium, or outlast the 20th century. The mission was 5 years. The spacecraft were built accordingly. Nobody predicted they would still be transmitting data in 2025. Nobody planned for that. Nobody budgeted for it. It simply happened because the engineering was honest. The redundancy was real, and the universe cooperated just enough. But they did not survive by accident. They survived because every component was built to last. Every backup system was tested, and every gram of plutonium was accounted for. And because a small team of engineers has spent nearly 5 decades keeping 2 machines alive across a distance that makes the word remote sound almost laughably inadequate. But they did not die. And what they discovered at the boundary, it began with a shock that no scientist had prepared for. Before a spacecraft can reach the heliopause, it must first cross something else, something violent, Something that the models predicted would appear at a specific distance and didn't. The solar wind, as it streams outward from the sun, is supersonic. Not supersonic in the way a fighter jet is supersonic, but supersonic in the plasma physics sense, moving faster than the speed at which pressure waves can propagate through the surrounding medium. From the sun's surface outward, the solar wind accelerates and travels at between 400 and 500 kilometers per second. It is a relentless, high-speed flood of charged particles racing in every direction at once. But it cannot maintain that speed forever. Eventually, as the solar wind approaches the region where interstellar pressure begins to assert itself, something has to give. The solar wind slams into a wall of its own, making a standing shockwave where it is forced to slow down almost instantaneously, dropping from 400 to 500 kilometers per second down to roughly 100 to 150 kilometers per second. The plasma compresses, it heats up dramatically, it becomes denser and more turbulent. Scientists call this boundary the termination shock. It is the first warning that the edge is near. The models predicted the termination shock would sit at roughly 75 to 90 astronomical units from the sun. That prediction was stated with considerable confidence. The physics was well understood. The calculations had been checked many times. 75 to 90 astronomical units, call it 6.9 to 8.3 billion miles, was where the solar wind would meet its match. Voyager 1 crossed the termination shock in December of 2004. At 94 astronomical units, it had already passed through the entire predicted range without triggering a crossing. The spacecraft had sailed past the outer boundary of the predicted zone and kept going before the shock finally arrived. But the distance was not even the strangest part. The strangest part was what happened before the final crossing. In 2002, Voyager 1's instruments detected unmistakable signs of the termination shock at 85 astronomical units. The plasma readings changed. The particle signatures shifted. Every indicator said the boundary is here. And then the boundary moved. It retreated outward, and Voyager 1 found itself back in undisturbed supersonic solar wind, as if the crossing had never happened. In 2003, the shock returned, washed over the spacecraft again, then pulled back once more. It took until December of 2004 for Voyager 1 to cross definitively and remain on the other side. The solar system's boundary was breathing. The termination shock was not a fixed wall. It was a dynamic surface, expanding and contracting in response to the sun's own activity cycle. The sun operates on an 11-year rhythm of increasing and decreasing magnetic activity. During periods of high activity, the sun produces stronger solar wind, and that increased pressure pushes the termination shock outward. During quieter periods, the wind weakens and the shock contracts inward. The boundary of our solar system moves steadily, measurably, in sync with the sun's heartbeat, like the walls of a lung expanding and collapsing with each breath. Then came Voyager 2. It crossed the termination shock on August 30th, 2007, at 84 astronomical units, approximately 930 million miles closer to the sun than where Voyager 1 had crossed. Two spacecraft, two different directions through space, two different crossing distances, separated by nearly 1 billion miles. If the heliosphere were the symmetric sphere that models predicted, both spacecraft should have crossed at roughly the same distance regardless of direction. They did not. That discrepancy was the first hard, direct, instrument-measured evidence that the heliosphere was not shaped the way anyone had drawn it. But that revelation would come fully into focus later. First, there was still the crossing itself to complete. Beyond the termination shock lies a region called the heliosheath. This is the zone between the slowed, heated, compressed solar wind and the heliopause itself, a churning, turbulent buffer filled with magnetic irregularities, plasma instabilities, and particles moving in chaotic directions. The models predicted the heliosheath would be 10 to 20 astronomical units thick. They predicted a spacecraft would take 5 to 10 years to cross it before reaching the heliopause. Voyager 1 took more than 8 years. It finally crossed the heliopause on August 25, 2012, at 121 astronomical units from the Sun, 11.2 billion miles. The models had predicted the heliopause at 90 to 100 astronomical units. The actual boundary was 2.4 billion miles farther out than the outer edge of that predicted range. To put that gap in perspective, 2.4 billion miles is greater than the distance from Earth to Uranus. The models were not off by a rounding error. They were off by an entire planet's worth of distance. The reason, analysis later confirmed, was that the local interstellar medium in our region of the galaxy is less dense than the models had assumed. The outward pressure pushing back against the heliosphere from outside was weaker than estimated. With less resistance from the interstellar medium, the solar wind was able to push the heliosphere's outer wall significantly farther before the two forces reached equilibrium. The heliosphere is larger than science believed, and that size matters enormously for life on Earth. A larger heliosphere means a more effective shield against galactic cosmic rays. Those rays, accelerated to near light speed by supernova explosions across the galaxy, constantly bombard the outer boundary of the heliosphere. The heliosphere deflects and weakens a substantial fraction of them before they can reach the inner solar system. A bigger shield means less cosmic ray penetration affecting atmospheric chemistry, influencing mutation rates in living organisms, and potentially shaping climate patterns across geological timescales. The size of the heliosphere is not an abstract number. It is a variable in the equation of life itself. But the distance being wrong was only the first part of the story. The shape of the heliosphere was what nobody could have imagined. The old model was elegant. A bubble, a sphere surrounding the sun in every direction at a roughly consistent distance, perhaps gently stretched in one direction, like a comet's tail, but fundamentally symmetric. Round, predictable, the kind of shape that fits cleanly into a textbook diagram and requires no further explanation. Reality had a different shape entirely. To understand why the heliosphere cannot be a sphere, you have to understand something about the sun that rarely comes up in casual conversation. The sun is not sitting still. Nothing in the galaxy sits still. The sun, along with every planet and moon and asteroid gravitationally bound to it, is moving through the Milky Way at approximately 490,000 miles per hour. That is not a typo. 490,000 miles per hour, tracing a vast orbit around the galactic center that takes roughly 225 million years to complete. From the sun's perspective, the interstellar medium is not a static environment. It is a headwind. A thin, cold, relentless stream of interstellar gas pressing into the front of the heliosphere from the direction the sun is traveling toward. The solar wind pushes outward in all directions equally, but the interstellar medium does not push back equally from all directions. It hammers into the front. It barely touches the sides and behind the sun, in the direction the solar system has already traveled through. The heliosphere stretches outward into a long trailing structure with far less external pressure to contain it. The front of the heliosphere, the region scientists call the nose, is compressed, squeezed inward by the constant headwind of interstellar gas. Voyager 1 was traveling in the general direction of the nose when it crossed the heliopause on August 25, 2012, at 121 astronomical units. That crossing distance reflected a compressed boundary pushed inward by the interstellar headwind acting directly against the sun's motion. Voyager 2 was traveling in a different direction toward what scientists call the flank, the side of the heliosphere where interstellar pressure is less direct, less concentrated. Voyager 2 crossed the heliopause on November 5, 2018, at 119 astronomical units, 2 astronomical units closer to the sun than Voyager 1. Despite heading toward a region that should be less compressed, 2 spacecraft, 2 very different trajectories through space, crossing distances separated by only about 186 million miles. That near equivalence across such different directions revealed a subtler asymmetry than anyone had anticipated. Not the dramatic elongation some models predicted, but a genuinely irregular, lopsided structure that resisted simple description. And then there is the tail, the direction behind the sun. The region the solar system has already passed through, where the heliosphere should stretch outward for potentially hundreds of astronomical units, trailing like the tail of an enormous comet moving through interstellar space. No spacecraft has ever measured it directly. No human instrument has ever sampled that region. The tail remains entirely theoretical, inferred from physics and indirect observation. Its true length and structure unknown. Indirect observation, however, has provided significant insight. In 2008, NASA launched a spacecraft called IBEX, the Interstellar Boundary Explorer. IBEX does not travel to the heliopause. It orbits Earth and looks outward, detecting a specific type of particle called energetic neutral atoms. These particles are created at the heliopause when charged solar wind particles exchange electrons with neutral interstellar atoms and become electrically neutral themselves, allowing them to travel in straight lines back toward Earth without being deflected by magnetic fields. By mapping where these particles come from and how energetic they are, IBEX can construct an indirect image of the heliopause from a distance of roughly 1 astronomical unit. What IBEX found confirmed what the Voyager crossings had suggested: the heliosphere is definitively asymmetric. The nose region is compressed. The tail region appears to extend significantly farther. The overall shape is not a sphere. It is not even the simple teardrop or comet shape that earlier models had proposed as a refinement of the sphere. In 2017, analysis of IBEX data suggested the heliosphere might be shaped more like a flattened crescent or a peanut shell in cross-section, a shape that no prior theoretical model had predicted and that required significant revision of existing frameworks to explain. The reason the heliosphere is shaped this way goes beyond just the sun's motion. The sun is currently traveling through a specific region of the local interstellar medium called the local interstellar cloud. This is a slightly denser pocket of interstellar gas a few light years across, and the boundaries of this cloud directly influence how the interstellar medium presses against the heliosphere from different directions. The cloud is not uniform. Its density varies. Its magnetic field has its own orientation. All of these local conditions shape the heliosphere from outside. The way a hand pressing unevenly against a balloon distorts it into something no longer round. And this is not a permanent configuration. The sun is moving. In the coming thousands of years, the sun will exit the local interstellar cloud and enter a different region of the interstellar medium with different density, different pressure, and different magnetic properties. When that happens, the heliosphere will change its size, its shape, its structure, all shifting in response to a new external environment. The heliosphere we are measuring today with Voyager and IBEX is a snapshot, a single frame from a very long film. The consequences of shape are not merely academic. The geometry of the heliosphere determines which directions galactic cosmic rays can penetrate most easily, at what intensities, and toward which parts of the inner solar system. A compressed nose means cosmic rays from that direction are more effectively blocked. An extended tail means cosmic rays may find easier entry from behind. Over millions of years of biological evolution on Earth, these directional variations in cosmic ray flux have influenced mutation rates, atmospheric chemistry, and climate in ways that science is only beginning to quantify. The heliosphere's shape is not just a curiosity of astrophysics. It is part of the story of how life on this planet became what it is. But the shape was only the surface layer inside the heliosheath. Voyager encountered a structure that existed in no equation, something no physicist had ever predicted would be there. In June of 2012, Voyager 1 was deep inside the heliosheath. By every model, every simulation, every theoretical framework that existed, it was still firmly inside the sun's territory. The heliopause was supposed to be somewhere ahead, still weeks or months away at minimum. The spacecraft was doing what it had been doing for years, plowing through the turbulent, heated, compressed plasma of the heliosheath, sending back data that broadly matched expectations for that region. Then something changed. The magnetic field readings stopped making sense in the heliosheath. The magnetic field behaves the way you would expect from a region of disturbed, slowed solar plasma, tangled, irregular, constantly shifting direction as turbulent plasma flows push and pull the field lines in every direction at once. That is the signature of the heliosheath. Organized chaos. The instruments on Voyager 1 had been reading exactly that for years. What they began reading in June of 2012 was something else entirely. The field lines were no longer tangled. They were straight, perfectly aligned, pointing radially outward from the sun in clean, parallel lines organized with a precision that had no business existing in the middle of a turbulent plasma region. The magnetic field had restructured itself into something that looked, in the data, less like the interior of a storm and more like a divided highway painted on an open road. And on those field lines, two things were happening simultaneously, in opposite directions. Solar plasma particles were streaming outward along the field lines, moving away from the sun. At the same time, galactic cosmic rays, high-energy particles from interstellar space, were streaming inward along the same field lines, moving toward the sun. Two opposing currents, two different populations of particles, one from inside the heliosphere and one from outside it, flowing in opposite directions on the same magnetic tracks at the same time. No model had predicted this. Not one. No theoretical paper had suggested this structure could exist. No simulation had produced it as an output. No physicist working on heliospheric boundary theory had included it in any published framework. It arrived in the data without warning, without precedent, and without explanation. Scientists named it the Magnetic Highway, and for a region that supposedly did not yet touch interstellar space. It was behaving in a way that suggested the boundary between two cosmic domains was far more porous, far more structurally complex than anyone had conceived. The leading explanation that emerged from subsequent analysis invokes a phenomenon called magnetic reconnection. At certain boundaries where two magnetic fields of different origins meet, field lines from each side can break apart and reconnect with field lines from the other side, forming continuous pathways that bridge the two previously separate magnetic domains. The current leading theory holds that inside the magnetic highway, the sun's magnetic field lines were connecting directly to the galactic magnetic field, creating physical bridges across what should have been an impenetrable boundary, and allowing particles from both sides to travel freely along those connected pathways in both directions simultaneously. Voyager 1 remained inside this magnetic highway for approximately 2 months, from June of 2012 through August of 2012. Throughout that entire period, the readings were consistent and unmistakable. Galactic cosmic ray intensity was elevated far above normal heliosheath levels. Solar plasma particle counts were depressed far below normal heliosheath levels. The spacecraft was sampling a region with direct physical access to interstellar space without having formally crossed the heliopause. Then, on August 25th, 2012, the transition completed. Solar plasma particles did not gradually fade. They essentially vanished over the course of a few days. Galactic cosmic rays simultaneously jumped to a new, higher, stable level. Every particle instrument on the spacecraft registered a definitive change, but the magnetic field did not rotate. This was the problem. In every model of the heliopause crossing, the magnetic field direction was expected to change as the spacecraft moved from the sun's magnetic domain into the galaxy's magnetic domain. Two different magnetic fields, two different sources, two different orientations. The crossing should produce a measurable rotation in field direction. It is perhaps the single most definitive signature of having crossed from one magnetic environment into another. Voyager 1 detected no such rotation. The field kept pointing in essentially the same direction it had been pointing throughout the heliosheath. And that absence triggered more than a year of genuine scientific debate within the community studying Voyager's data. Some researchers argued the particle data was unambiguous. The spacecraft had crossed. Others held that without the magnetic field rotation, the case could not be considered closed. Perhaps the heliopause had multiple layers. Perhaps Voyager was in some intermediate region with no precise equivalent in any existing theory. In September of 2013, NASA made the official announcement Voyager 1 had entered interstellar space on August 25, 2012. The reason the magnetic field had not rotated turned out to be a coincidence of pure geometry. The galactic magnetic field in that specific region of interstellar space happened to be oriented nearly parallel to the Sun's magnetic field at the point where Voyager 1 crossed. The two fields pointed in roughly the same direction. There was no rotation to detect because the two fields, by cosmic accident, were already aligned. Voyager 2's crossing on November 5th, 2018 told a cleaner story. The transition happened over approximately 1 day, dramatically faster than Voyager 1's prolonged and ambiguous approach, and Voyager 2's magnetometer recorded a clear rotation in field direction of approximately 20 degrees. Not a dramatic flip, but a measurable, unambiguous change, confirmation that the spacecraft had moved from one magnetic domain into another, the kind of direct evidence that settled any remaining doubts. The magnetic highway's significance extends beyond the specific events of 2012. It opened an entirely new area of research into how two plasma environments of completely different origins exchange material and energy at a shared boundary, a process with implications for plasma physics far beyond our own solar system. But even after crossing that boundary, Voyager 1 did not settle into a quiet interstellar environment. It began detecting enormous waves running through interstellar space, whose origin no one had thought to look for. Voyager 1 had crossed the heliopause. It was in interstellar space. The Sun's magnetic field was behind it. The Sun's plasma was behind it. By every definition that science had used for decades to describe the boundary between the solar system and the galaxy, Voyager 1 was on the other side. And then the Sun reached out and touched it anyway. In October and November of 2012, just weeks after the heliopause crossing, the plasma wave instrument aboard Voyager 1 detected something unexpected: oscillations, rhythmic vibrations moving through the plasma surrounding the spacecraft, sustained over a period of several weeks, with a frequency and character that did not match anything the instrument had recorded inside the heliosphere. The signal was not noise. It was not instrument error. It was real, structured, and propagating through the medium around the spacecraft in a way that demanded an explanation. The explanation, when scientists worked it out, was extraordinary. Earlier in 2012, the Sun had produced a powerful coronal mass ejection, ACME. These are eruptions from the Sun's surface that expel enormous clouds of magnetized plasma into space, moving at speeds far exceeding the ordinary solar wind. This particular ejection had traveled outward through the heliosphere, accelerating and interacting with the solar wind as it went. When it reached the heliopause, it did not simply stop at the boundary. The impact of that pulse against the heliopause launched a pressure wave, a shock wave into the interstellar medium on the other side. That wave propagated outward through the interstellar plasma at the local speed of sound in that medium, approximately 60 kilometers per second, slower than the solar wind, slower than the CME that created it, but fast enough to travel several astronomical units in a year, fast enough to reach Voyager 1 and register on its instruments. The Sun had thrown a stone into interstellar space. Voyager 1 detected the ripple. The wave detected in October and November of 2012 was the first. In April and May of 2013, Voyager 1's plasma wave instrument registered a second set of oscillations, a new wave, with a slightly different frequency than the first. Analysis traced it back to a different solar event. a separate period of intense activity on the sun that had occurred months earlier. The timing matched. The physics matched. A third wave arrived in March of 2014. A fourth followed in 2015, each one a delayed echo of a solar storm, traveling through a medium that science had assumed the sun could not reach. The frequency of each oscillation carried information beyond just confirming the wave's existence. By measuring the precise frequency at which the interstellar plasma vibrated as each wave passed through, scientists could calculate the local electron density of the medium surrounding Voyager 1. It is a technique borrowed from plasma physics. The natural oscillation frequency of a plasma depends directly on how many electrons are present per unit volume. Each wave, in essence, was ringing the interstellar medium like a bell, and the pitch of that ring revealed how dense the medium was at Voyager's location. Those density measurements served a second crucial purpose. They provided some of the most direct confirmation available that Voyager 1 had genuinely crossed into interstellar space. Inside the heliosphere, the plasma surrounding the spacecraft is solar in origin protons and electrons expelled by the sun, with a density and character specific to solar wind material. The oscillation frequencies measured by Voyager 1 after August of 2012 were consistent with interstellar plasma densities, not heliospheric ones. The bell was ringing at the right pitch for interstellar space. The spacecraft was measuring a medium that could only exist beyond the heliopause. None of this had been predicted. The scientific models that described the heliopause treated it as a wall of physical and electromagnetic boundary at which solar influence terminated. Solar wind particles stop at the heliopause. The sun's magnetic field is confined by the heliopause. These were the foundational assumptions of heliospheric theory, and they were broadly correct. But pressure is not the same as plasma. A solar storm does not need to send its particles across the heliopause to make itself felt on the other side. It only needs to push, and the heliopause, it turns out, transmits that push the way the surface of a drum transmits a strike, converting the impact into a wave that travels through whatever medium lies on the other side. The analogy is not perfect, but it is instructive. When an earthquake occurs deep inside the Earth, seismic waves radiate outward through the planet's layers. They travel through rock and mantle and crust, weakening with distance, but carrying information about their source for thousands of miles. The heliopause behaves similarly. A solar storm strikes it from the inside. The impact generates a wave that propagates through the interstellar plasma on the outside, carrying the sun's fingerprint into a region where the sun's material cannot go. Those waves do not travel forever. As they expand outward through the interstellar medium, their energy spreads across an ever-increasing volume of space. They weaken. Eventually, they dissipate entirely, absorbed into the background variations of the interstellar plasma. But before they fade, they can travel tens of astronomical units beyond the heliopause detectable by any instrument sensitive enough to read the faint oscillations in the surrounding plasma. The theoretical implications reach well beyond our own solar system. If the sun's storms can launch detectable shockwaves into interstellar space, then every star in the galaxy is doing the same thing. Every stellar flare, every coronal mass ejection from every one of the hundreds of billions of stars in the Milky Way is sending pressure waves outward into the interstellar medium surrounding it. The space between stars is not the silent, static void that early astronomers imagined. It is a medium constantly agitated by the collective activity of an entire galaxy's worth of stars, a vast interconnected ocean of plasma, in which every storm on every star sends ripples outward into the shared medium between them. The interstellar medium is alive with motion that has nothing to do with anything local. And if interstellar space was ringing with waves from solar storms, then the very material filling that space was far stranger than anything our calculations had prepared us for. Before Voyager, everything humanity knew about interstellar space came from a distance. Astronomers studied the spectra of starlight passing through interstellar gas clouds and inferred their chemical composition. Radio telescopes detected emissions from hydrogen atoms drifting between star systems and mapped their distribution across the galaxy. Theorists built mathematical models of the interstellar medium using those observations as inputs, calculating what the density, temperature, pressure, and magnetic field should be in the space between stars. The models were sophisticated. The observations were real. But none of it was direct. None of it was measurement from inside the medium itself. Voyager changed that. For the first time in human history, an instrument built on Earth was physically inside the interstellar medium, surrounded by it, sampling it in real time, not inferring it from light signals traveling across light years, not modeling it from equations derived from distant observations, measuring it directly. The way a thermometer measures the temperature of water, it is submerged in. What those instruments found was a medium that differed from the models in every property that could be measured. Not dramatically different in most cases, not wrong by orders of magnitude, but consistently, persistently, measurably off and off in ways that cascaded into significant consequences for everything downstream of those numbers. Start with density. The interstellar medium surrounding Voyager 1 measured approximately 0.08 particles per cubic centimeter. That is roughly 0.08 atoms, mostly hydrogen, some helium in every space the size of a sugar cube. The best vacuum chambers that human engineers have constructed in laboratories on Earth achieve densities of around 1 million particles per cubic centimeter. Interstellar space is more than 10 million times emptier than the finest vacuum we can manufacture with our most advanced equipment. By any everyday standard, it is as close to nothing as a physical medium can get, and yet it is not nothing. A single cubic meter of interstellar space, a volume roughly the size of a large household appliance, contains approximately 80,000 particles. They are extraordinarily sparse and extraordinarily cold in terms of their thermal energy budget. But they exist. They have mass. They have pressure. And as Voyager's data confirmed, even at that vanishing density, their collective pressure is sufficient to halt the entire outward flow of the sun's solar wind and force the formation of the heliopause. The temperature readings were stranger. Instruments indicated the local interstellar medium near the heliopause had temperatures ranging from roughly 30,000 to 50,000 degrees Fahrenheit. That number sounds violent. It sounds like the interior of a blast furnace. In everyday experience, 50,000 degrees Fahrenheit suggests something that would vaporize any material instantly. But temperature in a plasma does not mean what temperature means in a kitchen or a furnace. Temperature measures the average kinetic energy of individual particles, how fast they are moving. In a gas with normal density, high temperature means enormous numbers of fast-moving particles colliding constantly, transferring that energy as heat to anything they contact. In a medium with a density of 0.08 particles per cubic centimeter, there are almost no particles to collide with anything. The individual particles may be moving quickly, but there are so few of them that the total heat transfer rate is negligible. A human being placed in the interstellar space would not burn. They would freeze. The particles moving at 50,000 degrees would strike them so rarely that the heat delivered would be immeasurably small compared to the heat radiating away from the human body into the surrounding void. Pressure followed the same pattern of being technically present, but almost incomprehensibly small. The interstellar medium exerts a pressure of approximately 0.000000003 pascals. Earth's atmosphere at sea level presses down at roughly 101,300 pascals. The interstellar pressure is approximately 30 trillion times smaller. 30 trillion. And yet that pressure, that whisper of force from a medium so thin it barely qualifies as matter by ordinary standards, is precisely what holds the heliosphere in check. It is the external constraint that prevents the solar wind from expanding forever. The balance point between the sun's outward push and that nearly non-existent inward push is the heliopause. The most significant boundary in our solar neighborhood is maintained by a pressure differential that no instrument on Earth's surface could detect without extraordinary effort. The magnetic field measurement completed the picture. Voyager 2, which carried a functioning magnetometer across the heliopause in November of 2018, measured the interstellar magnetic field at approximately 0.4 nanotesla in the region just beyond the boundary. Earth's magnetic field at the surface measures roughly 50,000 nanotesla. The interstellar field near the heliopause is approximately 100,000 times weaker than the field that makes a compass needle point north. It is, by any intuitive standard, almost undetectably faint. But magnetic fields do not need to be strong to be consequential over vast distances, stretched across light years of space. Even a field of 0.4 nanotesla shapes the trajectories of charged particles moving through it, channeling galactic cosmic rays along its field lines, organizing the flow of plasma across interstellar distances, and connecting star systems to each other through a web of magnetic structure that spans the entire galaxy. Every one of these measured values differed from what the models had predicted, not by enormous factors in most cases, but consistently, and in the same direction. The interstellar medium was slightly less dense than estimated. The magnetic field slightly different in orientation than calculated. The pressure distribution not quite matching the assumed profile, small deviations. But small deviations in boundary conditions produce large deviations in outcomes. Those small differences in interstellar medium properties are what pushed the heliopause 2.4 billion miles beyond its predicted location. Those small differences in magnetic field orientation are what caused a year of scientific debate about whether Voyager 1 had actually crossed the boundary. Small numbers, enormous consequences. The data also revealed that the interstellar medium is not uniform. Density varies by 10 to 20% between locations separated by just a few astronomical units. Local pressure fluctuates with the structure of interstellar gas clouds drifting through that region of the galaxy. The medium is not a smooth, homogeneous fluid. It has texture. It has variations. And those variations mean that any spacecraft crossing from interstellar space must navigate a medium that changes character from one measurement point to the next. For anyone thinking seriously about interstellar travel, these measurements are not background science. They are engineering constraints. A spacecraft traveling at 10% of the speed of light, the minimum velocity that would make a journey to a nearby star achievable within a human lifetime, would encounter approximately 100 trillion hydrogen atoms per second, based on the density Voyager measured. Each collision at that velocity carries roughly 28 million times more energy than the equivalent collision at Voyager speed. The cumulative effect over years of travel would erode hull materials, damage electronics through radiation accumulation, and deposit continuous power loads of thousands of watts into the spacecraft's structure. Every number in that calculation depends directly on the density measurements Voyager 1 and 2 returned from interstellar space. Without those measurements, any interstellar mission design would be working from estimates that, as Voyager demonstrated, can be wrong in ways that matter enormously. But interstellar matter was only one layer of the picture. The deeper, stranger layer was the cosmic rays punching through that space from directions that nobody had anticipated. The galaxy is not peaceful. It never has been. Across the Milky Way, stars are dying in explosions so violent that for a few weeks, they outshine entire galaxies, pulsars. The collapsed remnants of those dead stars spin hundreds of times per second, flinging magnetized winds outward at near light speed. Black holes devour surrounding matter and release jets of energy that stretch for thousands of light years. The galaxy is an engine of continuous violence, operating on a scale that makes every storm, every earthquake, every nuclear weapon ever detonated on Earth look like background noise. And all of that violence produces something that travels silently through the galaxy in every direction, including straight toward us. Galactic cosmic rays are the fastest moving matter in the universe. They are not light. They are not radiation in the electromagnetic sense. They are actual particles, mostly protons, the nuclei of hydrogen atoms. along with helium nuclei and heavier atomic nuclei stripped of their electrons, accelerated to velocities approaching the speed of light by the shock waves of supernova explosions, by the winds of rapidly spinning pulsars, and by other high-energy events scattered throughout the galaxy. They travel in straight lines until a magnetic field bends their path. They pass through walls. They pass through bodies. They pass through planets. Only the most massive shielding can stop the most energetic of them. Their energies span an almost incomprehensible range. The lower end sits at millions of electron volts. The upper end reaches into the trillions of electron volts and beyond. The most energetic cosmic rays ever detected carry more energy in a single subatomic particle than a baseball thrown at nearly 100 miles per hour. Some individual cosmic ray particles carry energies that exceed by significant factors. Anything the Large Hadron Collider at CERN, the most powerful particle accelerator ever built by human beings, can produce in a controlled laboratory setting. These particles are not created by machines. They are created by the most catastrophic events in the observable universe, and they have been traveling through the galaxy for thousands or millions of years before arriving at the boundary of our solar system. The heliosphere has been deflecting them the entire time. As Voyager 1 moved outward through the heliosheath in the years before crossing the heliopause, its cosmic ray detectors recorded a gradual and steady increase in galactic cosmic ray intensity. This matched predictions. The deeper a spacecraft moves into the heliosheath, the weaker the heliosphere's shielding effect becomes, and the more galactic cosmic rays can penetrate. The trend was expected. The instruments confirmed it. What happened after Voyager 1 crossed the heliopause in August of 2012 was also partly expected. Cosmic ray intensity jumped to a new, higher stable level approximately 10 to 20% more intense than readings taken inside the heliosheath. That jump confirmed something important. The heliosphere is a genuine physical shield against galactic cosmic rays. Even the outermost, most turbulent layers of the heliosphere, billions of miles from the Sun, reduce the cosmic ray flux reaching the inner solar system by a measurable and significant amount. The heliosphere is not merely the region where the Sun's wind flows. It is an active radiation barrier, maintaining conditions inside that are meaningfully different from the interstellar environment outside. But the directional distribution of those cosmic rays was not what the models expected. Not at all. The standard assumption was straightforward: galactic cosmic rays should arrive at the heliopause from roughly all directions with approximately equal intensity. The galaxy surrounds us on every side. Cosmic ray sources, supernova remnants, pulsar wind nebulae, active galactic regions are distributed throughout the galaxy in all directions. Simple reasoning suggested the flux arriving at our solar system should be more or less isotropic, uniform. A sphere of incoming particles hitting the heliosphere evenly from every angle. Voyager's instruments recorded something different. There was a clear directional anisotropy. Specific directions showed higher cosmic ray intensities. Others showed lower intensities, and the pattern did not match the distribution of known sources in any straightforward way. The cosmic rays were not arriving equally from all directions. They were arriving preferentially from some directions and relatively sparsely from others, in a pattern that revealed previously unknown structure in the local interstellar environment and in the galactic magnetic field that threads through it. The most counterintuitive finding involved the direction of the galactic center, the center of the Milky Way, the densely packed central bulge where star density is highest, where supernova explosions are most frequent, where the most energetic processes in the galaxy are concentrated, should logically be the strongest source of galactic cosmic rays reaching our location. More supernovae means more acceleration events. More acceleration events means more cosmic rays produced and sent outward through the galaxy. Simple logic suggested the galactic center direction should show the highest cosmic ray intensities. It did not. Cosmic ray intensity from the direction of the galactic center was lower than expected. The current leading explanation is that the galactic magnetic field is significantly stronger in the inner regions of the Milky Way than in our outer neighborhood. Cosmic rays produced near the galactic center encounter dense, powerful magnetic fields that trap and scatter them, preventing efficient outward propagation. The magnetic field acts as a cage, keeping the most energetically rich region of the galaxy from freely exporting its cosmic rays to the outer arms where our solar system resides. The particles are produced in enormous quantities near the center, but the magnetic environment there prevents most of them from reaching us. The consequences of cosmic rays for Earth are not abstract. When galactic cosmic rays penetrate the heliosphere and reach Earth's upper atmosphere, they collide with nitrogen and oxygen nuclei and produce showers of secondary particles, including neutrons that convert atmospheric nitrogen into carbon-14. That carbon-14 is the foundation of radiocarbon dating. Every archaeological date derived from organic material depends ultimately on a process driven by galactic cosmic rays. Beyond that, there is ongoing scientific research into whether cosmic ray flux variations influence cloud formation in Earth's atmosphere, potentially affecting climate on timescales of decades to centuries. Over geological timescales, periods of higher cosmic ray exposure caused by the sun passing through denser interstellar regions or by nearby supernova explosions reducing heliospheric shielding may have influenced mutation rates in living organisms, contributing to evolutionary pressures across millions of years of biological history. Every calculation connecting cosmic ray flux to these Earth-scale consequences requires knowing the actual intensity and directional distribution of cosmic rays in true interstellar space. Before Voyager, those values were estimates derived from indirect observation. After Voyager, they are direct measurements taken inside the medium itself. The baseline has been established. The reference point exists. Future models of cosmic ray influence on Earth's climate, chemistry, and biology will be built on data that only 2 aging spacecraft traveling on borrowed power made possible. But while those cosmic rays were punching through interstellar space, the 2 small spacecraft measuring them were running out of time, their power fading year by year, and no one knowing how much longer they could keep talking. There is a law in physics that does not negotiate. It does not respond to budgets, or schedules, or the scientific value of the data still waiting to be collected. It simply operates continuously and without exception at the same rate it has always operated since the universe began. Plutonium-238 decays every 87.7 years. Half of whatever plutonium remains converts into uranium-234 and releases heat in the process. That heat is what powers Voyager, and that heat is diminishing at a rate of approximately 4 watts per year, every year, with the same inevitability as the turning of the Earth. In 2025, nearly 48 years have passed since launch. The plutonium in Voyager, one's 3 radioisotope thermoelectric generators, has been decaying the entire time. What began as 470 watts of electrical output at launch has fallen to approximately 249 watts. That number sounds like there is still margin to work with. There is not. The total power required to keep Voyager 1's core systems running, the computers, the transmitter, the heaters preventing critical components from freezing solid, and at least a handful of science instruments, sits at approximately 245 to 248 watts. The gap between what the spacecraft has and what it needs is measured in single digits. A few watts? Less margin than a string of holiday lights. Every decision NASA makes about Voyager 1's power budget is irreversible in the most literal sense. When engineers turn off a heater to save electricity, the component it was protecting drops to the ambient temperature of a deep space, roughly negative 450 degrees Fahrenheit. At that temperature, materials behave differently than their designers intended. Lubricants solidify, seals contract. Electronics that were designed to operate within specific temperature ranges find themselves far outside those ranges, and there is no guarantee they will function correctly if power is ever restored. In most cases, turning something off means it is off permanently. The triage is one-directional. The cameras were the first major sacrifice. On February 14th, 1990, Voyager 1 turned its camera platform toward the inner solar system one final time and took a series of images that would become among the most famous photographs in human history. Then the cameras were powered down permanently, freeing their electricity allocation for systems that still had work to do. The last image captured was a pale blue dot suspended in a beam of scattered sunlight Earth from approximately 3.7 billion miles away, occupying less than a single pixel in the frame. The power management decisions that followed over the subsequent decades were exercises in engineering discipline that have almost no parallel in the history of spacecraft operations. In 2020, NASA shut off the heater protecting the cosmic ray instrument aboard Voyager 2. The instrument's temperature dropped to negative 74 degrees Fahrenheit, 40 degrees below its design operating limit. Every engineering principle suggested it should fail. Every reasonable expectation said the instrument would stop functioning within days. Instead, it kept working. The data kept coming. Hardware designed and built in the early 1970s, operating at conditions its creators never intended it to survive, continued performing its function without interruption. There is no elegant technical explanation for why. It simply worked, because the engineers who built it well. Then came 2023. For months, Voyager 1 began transmitting data that was unintelligible. Garbled sequences that the Deep Space Network received clearly, but could not decode into usable scientific or engineering information. The signal strength was normal. The transmission format was correct, but the content made no sense. Engineers at NASA's Jet Propulsion Laboratory spent months analyzing the problem from a distance of more than 14 billion miles, with every diagnostic query requiring more than 22 hours to reach the spacecraft and another 22 hours for any response to return. The round-trip time for a single question and answer was more than 44 hours. Patient, methodical troubleshooting eventually identified the source, a single corrupted memory chip in the flight data system computer, the component responsible for packaging science and engineering data before transmission. The chip could not be replaced. It could not be repaired remotely. What it could be done was worked around. Engineers wrote new software that redistributed the data previously stored in that corrupted chip across other available memory locations in the computer, a solution that required understanding the internal architecture of a machine built more than 50 years ago. Writing code compatible with that machine's 1970s processor, transmitting the patch across 14 billion miles of space, and waiting nearly 2 days to learn whether it had worked. In April of 2024, coherent data began flowing again from Voyager 1. The patch had worked perfectly throughout 2024 and into 2025. NASA has continued making the slow, calculated decisions that define Voyager's final operational chapter. Non-essential systems have been powered down one by one. The priority is absolute and unwavering. Preserve the instruments measuring the interstellar magnetic field and plasma environment for as long as physically possible. These are the instruments with no replacement, measuring an environment no other spacecraft has ever reached, returning data that cannot be obtained any other way. Everything else is secondary to keeping those sensors alive and transmitting. The timeline ahead is written in physics and cannot be rewritten, sometime between 2025 and 2027. Additional science instruments will need to be shut down as the power budget contracts further. Around 2030, possibly 2032 at the latest, the remaining power will be insufficient to run the transmitter at the strength required to send a signal that Earth's antennas can detect. On some unremarkable day within that window, the Deep Space Network will receive a signal from Voyager 1, and then another, and then silence. Not a dramatic failure, not an explosion, just silence, gradually indistinguishable from the background noise of the universe. The spacecraft will not stop. There is nothing in interstellar space to slow it down. no atmosphere, no friction, no gravitational drag significant enough to matter on human timescales. Voyager 1 will continue traveling at 38,000 miles per hour in the direction it is already heading, carrying its instruments and its antenna and its empty RTG casings through the interstellar medium forever, or until something collides with it, which in the emptiness of interstellar space may not happen for longer than the current age of the universe. It will keep going. Silent and dark, carrying one thing that was never meant to speak to us at all. And when those spacecraft finally go silent, they will carry something with them. Something designed to last for billions of years and speak on behalf of all of humanity. The decision to attach a message to the Voyager spacecraft was not inevitable. It was argued over, lobbied for, and very nearly left out entirely given the compressed timeline of mission preparation. Carl Sagan, the astronomer and science communicator who became the driving force behind the project, had to make the case that sending a spacecraft beyond the solar system without any representation of the civilization that built it would be a missed opportunity of cosmic proportions. He won that argument, and what resulted from winning it was one of the strangest, most ambitious, and most philosophically serious creative projects in human history. Each Voyager carries a golden record, a 12-inch disc of copper plated with gold. Gold was chosen for a specific reason. It does not oxidize. It does not corrode. In the vacuum of space, with no oxygen and no moisture and no chemical agents to attack the metal, a gold-plated surface can remain intact essentially indefinitely. The record is designed to last for billions of years, not as a metaphor, but as a genuine engineering specification. The information it carries is not stored magnetically, which degrades over time, and not stored electronically, which requires power to read. It is physically inscribed into the surface of the disk in analog grooves, the same fundamental principle as a vinyl record. The information will remain readable as long as the physical surface remains intact, independent of any power source or compatible technology. What is on that record is the answer to one of the hardest questions ever put to a committee of human beings. If you had a single object, carried by a spacecraft that might drift through the galaxy for billions of years before anyone found it, to tell an unknown intelligence everything that matters about your species, what would you put on it? The natural sounds of Earth came first. Ocean waves breaking on a shore, rain falling through leaves, thunder rolling across an open sky, a volcanic eruption, low and reverberant, the songs of humpback whales, those long, complex, haunting vocalizations that travel hundreds of miles through ocean water, birds, crickets, frogs. These were chosen to represent the living world, that humans share the planet with the context in which human civilization developed. Then the sounds of human life itself, a newborn crying, that universal signal of new life arriving in the world, footsteps, laughter, a heartbeat, the sound of a mother kissing a child. The music selection was perhaps the most contested part of the entire project. 27 musical works were chosen to represent the breadth of human musical expression across cultures and centuries. Johann Sebastian Bach's Brandenburg Concerto No. 2, a piece of mathematical architecture built from sound, representing the Western classical tradition at its most precise and emotionally complex. Ludwig van Beethoven's Fifth Symphony, a string quartet, Mozart, Stravinsky. But the committee knew that representing only Western classical music would be a profound failure of the project's stated purpose. The record also carries gamelan music from Java, with its intricate, interlocking rhythms, blues from the American South, music born from suffering and resilience, carrying emotional truth that transcends its cultural origins, jazz from Louis Armstrong, whose trumpet and vocals represent an art form that grew from the specific history of a specific people in a specific country and became universal. Rock and roll from Chuck Berry, whose guitar carried the energy of mid-20th century American youth culture into a form that spread across the world within a generation. choral music from Georgia, panpipe music from Peru, shakuhachi from Japan, Indian classical music with its intricate rhythmic structures, Aboriginal songs from Australia, representing some of the oldest continuous musical traditions on the planet. Greetings in 55 languages were recorded and encoded, spanning from ancient Akkadian, a language extinct for thousands of years, spoken in what is now Iraq, to Mandarin Chinese, Spanish, Hindi, Arabic, and English, each greeting brief, each one expressing some variation of the same fundamental sentiment: we are here. We wish you well. We hope someday to know you. 116 images were encoded as audio signals translated into patterns of sound that, when decoded correctly, reconstruct as visual images, mathematical definitions, physical units of measurement, the structure of DNA, the architecture of the solar system, maps of Earth's continents, the human body, faces from many cultures, a family eating a meal, children playing, people working, architecture from across human history, food, a highway, a supermarket, the full complexity of human civilization compressed into 116 frames. The pulsar map is perhaps the most purely scientific element of the record, designed by Frank Drake, the astronomer who pioneered the scientific search for extraterrestrial intelligence. It shows the positions of 14 pulsars relative to the Sun, along with the precise rotational period of each. Pulsars are rotating neutron stars that emit radio pulses at extraordinarily regular intervals. Natural clocks with known, measurable rates of change over time, because each pulsar has a unique period, and because those periods decrease at known rates as the pulsar loses energy. The map functions simultaneously as a location identifier and a timestamp. Any civilization capable of detecting radio emissions from pulsars could use the map to determine exactly where in the galaxy the record originated and approximately when it was created. Carl Sagan led the overall project. Anne Druyan, who would later become his wife, oversaw the selection of sounds and music, making hundreds of decisions about what to include and what to leave out, each one a small act of choosing what humanity is. Frank Drake designed the pulsar map. Linda Saltzman Sagan drew the figures of a man and woman on the record's aluminum cover, human forms shown in the proportions and postures of 1977 American adults, greeting whoever might someday hold the disc. The probability that the golden record will ever be found by anyone is, by any honest calculation, essentially zero. The galaxy contains hundreds of billions of stars. The volume of space between them is incomprehensible. The two Voyager spacecraft are tiny objects moving at speeds that are impressive by human standards and negligible by galactic ones. In 40,000 years, Voyager 1 will make its closest approach to another star system, passing within 1.6 light-years of a star called Gliese 445, and that passage will be far too distant to bring the spacecraft within any reasonable detection range of anything orbiting that star. The record will not be found, almost certainly forever. But the probability of discovery was never the point. The golden record was never primarily about communication with another civilization. It was about the act of asking the question. For the first time in human history, a species was forced to look at itself clearly enough to answer, what are we, stripped of politics and geography and history and conflict, reduced to what we actually are at our core. What sounds define us? What music represents us? What images show who we are rather than who we wish we were? The answer is pressed into gold and traveling through interstellar space at 38,000 miles per hour. It will outlast every building humanity has ever constructed. It will outlast every book, every digital archive, every monument. If the sun expands and consumes the Earth in 5 billion years, the golden record will still be drifting through the galaxy, intact, carrying the sound of ocean waves and a mother's kiss, and Chuck Berry's guitar into a darkness no one from Earth will ever see. But While the golden record carried humanity's memory out into the universe, Voyager's discoveries were raising a far larger question: whether we truly understood the home we were leaving behind. Before either Voyager spacecraft reached the edge of the solar system, before they crossed the termination shock or discovered the magnetic highway or sampled the interstellar medium directly, they did something else entirely, something that would have been considered a complete and historic success even if they had gone silent immediately afterward. They flew through the outer solar system and revealed worlds that humanity had been staring at for centuries without ever actually seeing. The first destination was Jupiter. Voyager 1 arrived in March of 1979. Voyager 2 followed in July of the same year. What they found bore almost no resemblance to what Earth-based telescopes had suggested. The most dramatic discovery came not from Jupiter itself, but from one of its moons. Io, the innermost of Jupiter's 4 large Galilean moons, was expected to be geologically dead. A cold, cratered body, similar to Earth's moon, passive and ancient. A navigation engineer named Linda Morabito was examining Voyager 1 images to determine the spacecraft's precise position when she noticed something extending from Io's edge that had no business being there. An umbrella-shaped plume, rising hundreds of miles above the surface. An active volcanic eruption. The first active volcano ever discovered anywhere beyond Earth. Io turned out to be the most volcanically active body in the entire solar system. The energy driving that activity was not radioactive decay in the moon's interior, the standard mechanism powering geological activity on rocky planets. It was tidal heating. Jupiter's enormous gravitational field, combined with the gravitational tugs of neighboring moons Europa and Ganymede, constantly flexes and squeezes Io's interior as the moon follows its slightly elliptical orbit. That flexing generates friction. Friction generates heat. Heat melts rock, and melted rock erupts through hundreds of volcanic vents across a surface that is being continuously resurfaced, erasing craters almost as fast as they form. That single discovery, tidal heating, as a geological power source, changed everything about how scientists think about energy in the outer solar system. If gravitational flexing can power volcanism on Io, it can power internal warming elsewhere? And that realization opened a door that has never closed. Europa, the next moon outward from Io, told a completely different story with equally profound implications. Its surface was smooth ice, fractured into complex patterns of cracks and ridges, with almost no impact, craters indicating a young surface being continuously renewed from below. Long linear fractures called lineae stretched for hundreds of miles. Regions of chaotic terrain showed where the ice appeared to have broken apart and refrozen in disordered patterns, as if something beneath it had been moving. The implication, once the tidal heating principle was understood, was direct and staggering. Beneath that frozen surface, Europa might harbor a liquid water ocean, kept from freezing by the same gravitational kneading that keeps Io erupting. An ocean of liquid water beneath the ice in the outer solar system. The later Galileo mission in the 1990s and 2000s would provide strong magnetic evidence confirming that conducting layer exists beneath Europa's surface. But Voyager provided the first visual evidence, the first suggestion that life-sustaining liquid water might exist somewhere other than Earth. Voyager 1 also confirmed in 1979 that Jupiter has a ring system. Faint, thin, composed of microscopic dust particles rather than the ice chunks that make Saturn's rings spectacular. Astronomers had suspected rings might exist based on indirect evidence, but had never detected them from Earth. Their confirmation proved that ring systems are not unique to Saturn. Giant planets, it appeared, collect debris into rings as a natural consequence of their gravitational reach. Saturn received Voyager 1 in November of 1980, and Voyager 2 in August of 1981. Saturn's rings had been known since the 17th century, but their true nature was entirely hidden from Earth-based observation. What Voyager revealed was not rings, but a system of extraordinary complexity. Thousands of individual ringlets nested within the broad bands visible from Earth, separated by gaps created by gravitational resonances with Saturn's moons, structured by density waves and bending waves propagating through the ring material like sound waves through a medium. Shepherd moons orbited at ring edges, their gravity herding ring particles into sharp boundaries. The rings were thousands of miles across, yet in most places only about 30 feet thick thinner, proportionally, than a sheet of paper scaled to the size of a football field. Titan, Saturn's largest moon, drew Voyager 1 into a close flyby that cost the spacecraft its trajectory to Uranus and Neptune, a sacrifice the science team considered worthwhile. Titan's atmosphere turned out to be denser than Earth's, with a surface pressure approximately 1.5 times what a person standing at sea level on Earth experiences. The composition was primarily nitrogen, with methane and complex organic compounds forming a thick orange photochemical haze that completely obscured the surface from Voyager's cameras. The organic chemistry occurring in Titan's atmosphere, driven by sunlight breaking down methane into more complex hydrocarbons, resembled in some respects the chemistry theorized for early Earth before life began. The Cassini-Huygens mission, arriving decades later, would confirm what Voyager's atmospheric data suggested: a world with lakes and seas of liquid methane, river channels carved by methane rain, and dunes made of organic sand, the only place beyond Earth where liquids flow across the surface. Though those liquids are hydrocarbons rather than water, Voyager 2 continued alone to Uranus, arriving in January of 1986. Uranus proved deeply strange. Its rotational axis is tilted 98 degrees relative to its orbital plane, meaning the planet essentially rolls along its path around the Sun like a barrel on its side rather than spinning upright like a top. Each pole alternates between 42 years of continuous sunlight and 42 years of complete darkness. 10 previously unknown moons were discovered, along with 2 new rings. Miranda, one of Uranus's moons, displayed geology that defied easy explanation: ancient cratered terrain sitting directly adjacent to grooved regions of parallel ridges and valleys, interrupted by cliffs estimated at 6 miles high, nearly twice the depth of the Grand Canyon multiplied by 3. Something catastrophic had shaped Miranda, though exactly what remains an active question. Neptune waited at the end. Voyager 2 arrived in August of 1989, nearly 12 years after launch. Neptune was expected to be a quieter, blander version of Uranus. It was anything but. A storm system the size of Earth. The Great Dark Spot churned across its blue surface. Winds exceeded 1,300 miles per hour, the fastest measured on any planet in the solar system. Triton, Neptune's largest moon, orbited in the wrong direction. Retrograde, opposite Neptune's rotation, a near certain sign that it was captured from the Kuiper Belt rather than formed alongside its host planet. And despite a surface temperature of negative 391 degrees Fahrenheit, Triton had active geysers, erupting nitrogen gas that carried dark particles aloft before they fell back as streaks across the frozen surface. Voyager returned more data about the outer solar system than every previous observation in human history combined: active volcanism, hidden oceans, ring complexity, organic chemistry, impossible geology, retrograde moons with active geysers. Every world was stranger than expected. But all those magnificent worlds, Jupiter, Saturn, Titan, Neptune, were only stopping points. The true destination of the journey was what lay ahead, and no map could have prepared anyone for it. There is a common misconception worth addressing directly. When Voyager 1 crossed the heliopause in August of 2012 and entered interstellar space, many people assumed the spacecraft had left the solar system. In one important sense, that is true. It had exited the heliosphere, the region dominated by the sun's wind and magnetic field. But the solar system is not defined only by the reach of the solar wind. It is defined by the reach of the sun's gravity, and by that measure, Voyager 1 has not left the solar system. It will not leave the solar system for an extraordinarily long time. Surrounding the known planetary region of the solar system, extending far beyond the heliopause, is a vast theoretical structure called the Oort cloud. It is not a cloud in any familiar sense, not a concentrated region of gas or dust visible to telescopes. It is an enormous, roughly spherical shell of icy bodies, comets, planetesimals, frozen remnants from the early solar system, orbiting the Sun at distances ranging from approximately 2,000 astronomical units at the inner edge to roughly 100,000 astronomical units at the outer edge. 100,000 astronomical units. That outer boundary sits approximately halfway between the Sun and the nearest star. No spacecraft has ever reached the Oort cloud. No instrument has ever directly observed it. Its existence is inferred entirely from the behavior of long-period comets with orbital periods of hundreds or thousands of years that arrive from random directions in the sky, tracing trajectories back to a reservoir at enormous distances. The Oort cloud is the only structure consistent with those observed trajectories. It is almost certainly real, but we have no direct measurements of it, no images of its constituent objects, no data from instruments inside it. Voyager 1, traveling at 38,000 miles per hour, will not reach the inner edge of the Oort cloud for approximately 300 years. 3 centuries of continuous travel at that speed, just to arrive at the beginning of a structure that is itself tens of thousands of astronomical units thick, and to exit the outer edge of the Oort cloud to travel beyond the Sun's gravitational sphere of influence entirely, will take approximately 30,000 years. 30,000 years. The last ice age ended roughly 11,500 years ago. Agriculture began approximately 10,000 years ago. All of recorded human history fits within a span shorter than half the time. Voyager 1 will spend, still technically within the solar system, after its transmitters have gone permanently silent. The Oort cloud exists in a peculiar in-between state. It lies entirely within the Sun's gravitational territory. Every object in it is gravitationally bound to the Sun, orbiting it on timescales of millions of years, but it lies entirely outside the heliosphere, outside the Sun's wind, outside the Sun's magnetic field. Galactic cosmic rays flow through it freely. The interstellar medium penetrates it without resistance. The conditions there are interstellar in character, even though the objects present are gravitationally solar. It is a zone where the Sun's gravity persists long after its physical influence has faded, a ghostly dominion extending halfway to the stars. The nearest star to our Sun is Proxima Centauri, a dim red dwarf located 4.24 light-years away. In more immediate terms, that distance is approximately 268,000 astronomical units. 268,000 times the distance from Earth to the Sun. At Voyager 1's current speed, reaching Proxima Centauri would require approximately 73,000 years. And Voyager 1 is not traveling toward Proxima Centauri. It is heading in a completely different direction, toward the constellation of Fucus. The star it will pass closest to in the foreseeable future is Gliese 445, which it will approach to within 1.6 light-years in approximately 40,000 years. 1.6 light-years is approximately 9.4 trillion miles. That is not a close approach in any meaningful sense. It is simply the nearest any star happens to lie to Voyager 1's trajectory across the next several tens of thousands of years. Voyager 2 is heading towards the constellation Pavo and Indus. In approximately 40,000 years, it will pass within 1.7 light-years of the star Ross 248. Again, not close enough for any gravitational interaction, not close enough to enter any planetary system that might orbit that star, simply a passage through the vast emptiness between stellar systems at a distance that would be invisible to any observer at the destination. After those closest approaches, both spacecraft will continue wandering the galaxy indefinitely, their trajectories gradually altered over millions of years by the gravitational influences of stars they pass at varying distances. On timescales of hundreds of millions of years, they will complete orbits of the galactic center alongside the stars of the Milky Way, each orbit taking approximately 225 million years to complete. They will do this essentially forever, or until some collision or gravitational encounter eventually alters their fate in ways impossible to predict across such timescales. The distances involved make the idea of interstellar travel with any technology remotely connected to what we currently possess essentially impossible within any meaningful human time frame. Reaching Proxima Centauri in a time span compatible with a human lifetime or even a human civilization's sustained attention requires traveling at no less than 10% of the speed of light. 10% of the speed of light is approximately 67 million miles per hour. Voyager 1 travels at 38,000 miles per hour. The ratio between those two numbers is approximately 1,760 to 1. A spacecraft traveling at 10% of light speed would cover the distance to Proxima Centauri in approximately 42 years, achievable, theoretically, within a human career. But the gap between 38,000 miles per hour and 67 million miles per hour represents a challenge in propulsion, power, and engineering that no current technology approaches. The scale of the solar system, revealed fully only by tracking where Voyager has traveled and how long it has taken to get there, reframes every intuitive sense of distance that human experience provides. 48 years of travel, 38,000 miles per hour, continuously, without slowing, and the spacecraft is barely past the doorstep. And if we ever want to send something truly to the stars, Voyager's discoveries had already drawn a far harsher picture than anyone expected of what waits out there. Voyager's data is not merely a record of what exists at the edge of the solar system. It is a document of constraints, hard, physical, non-negotiable constraints that apply to any object moving through interstellar space at any speed, built by any civilization, using any technology. Before Voyager, those constraints were estimated from indirect observation and theoretical modeling. After Voyager, they are measured, and the measurements are sobering in ways that no amount of optimism about future technology can simply wish away. The first constraint is atomic collision. At Voyager's speed of 38,000 miles per hour, the interstellar medium is essentially transparent. The spacecraft occasionally encounters a hydrogen atom, and the impact carries so little energy that the cumulative effect over decades of travel is negligible. The spacecraft's hull experiences no meaningful erosion. The electronics suffer no meaningful damage from the physical impact of interstellar atoms. At Voyager's speed, the medium that Voyager measured approximately 0.08 atoms per cubic centimeter is as close to nothing as makes no practical difference. At 10% of the speed of light, everything changes. The kinetic energy of a collision scales with the square of the velocity. 10% of light speed is approximately 67 million miles per hour, roughly 1,760 times faster than Voyager. The energy delivered by each hydrogen atom collision at that speed is approximately 28 million times greater than the equivalent collision at Voyager's velocity. A spacecraft with a cross-section of 1 square meter traveling at 10% of light speed through the interstellar medium, Voyager measured would intercept approximately 100 trillion hydrogen atoms per second. Each collision delivers a tiny amount of energy, 100 trillion of them per second, sustained over years or decades, adds up to continuous power deposition of thousands of watts into the spacecraft's hull, appearing as heat, as material erosion, as damage to crystal structures at the atomic level. Hull materials would be gradually abraded away. Electronics embedded near the surface would accumulate radiation damage from the cascades of secondary particles produced by each high-energy impact. The spacecraft would be slowly eaten alive by the medium it was traveling through, and every number in that calculation comes directly from the density measurements Voyager returned from interstellar space. The second constraint is radiation. Voyager's cosmic ray instruments measured galactic cosmic ray intensity in true interstellar space at approximately 10 to 20% higher than inside the heliosheath and already significantly elevated compared to the inner solar system. A spacecraft on a decades-long interstellar journey would accumulate cosmic ray exposure continuously throughout the trip, with no heliosphere providing any shielding whatsoever. For electronics, this means progressive radiation damage to transistors and memory cells, the same type of damage that corrupted Voyager 1's memory chip in 2023. But occurring at higher dose rates, in more sensitive modern components, over far longer timescales for any human crew, the implications are more severe. Cosmic ray exposure at interstellar levels over a 42-year journey to Proxima Centauri would deliver radiation doses that current medical understanding considers incompatible with acceptable cancer risk by any existing regulatory standard. Heavy shielding is the only answer, and heavy shielding means enormous mass, which means enormous energy requirements to accelerate that mass to the required speed. The constraints compound each other. The third constraint is power. Voyager's RTGs lose 4 watts per year. Over 48 years, that decay has reduced output from 470 watts to approximately 249 watts, a mission designed to last 100 years. The minimum plausible duration for a crewed interstellar journey, even at speeds far beyond Voyager's, cannot rely on RTG technology in any form that currently exists. The power requirements for propulsion, life support, communication, and scientific operations over such a time frame demand energy sources of a fundamentally different character. Nuclear fission reactors capable of operating in deep space for a century are theoretically possible, but have never been built or tested for anything approaching that duration. Nuclear fusion, which would provide far greater energy density, remains a technology that has not yet achieved sustained net energy output in any laboratory on Earth, let alone in a form suitable for space propulsion. The fourth constraint is communication. A signal traveling at the speed of light from a spacecraft at Proxima Centauri takes 4.24 years to reach Earth. A response takes another 4.24 years to return. The round-trip communication time for a single exchange is more than 8 years. No real-time control of any kind is possible across interstellar distances. Every decision the spacecraft makes, every navigation correction, every system response to an unexpected situation, every scientific choice about where to point instruments must be made autonomously by systems aboard the spacecraft, without any possibility of human input from Earth on any timescale shorter than years. The autonomy requirements for an interstellar spacecraft exceed by enormous margins anything that has ever been built. Voyager operates with human oversight despite its 22-hour one-way signal delay. An interstellar spacecraft cannot. The fifth constraint is the environment itself. Voyager demonstrated that interstellar space is not static. Shock waves from solar storms propagate through the interstellar medium. The density varies by 10 to 20% over distances of a few astronomical units. The magnetic field changes direction between measurement points separated by only about 100 astronomical units. Other stars are producing their own pressure waves and plasma outflows into the interstellar medium, through which any spacecraft must travel. An interstellar mission must be designed not for a smooth, predictable medium, but for a dynamic, variable environment that no spacecraft will encounter in exactly the form that any pre-mission measurement recorded. These are not theoretical objections to interstellar travel. They are engineering specifications derived from actual measurements. And they are precisely why the scientific community takes them seriously when designing the next generation of deep space exploration concepts. NASA's Interstellar Probe concept is the most developed formal response to what Voyager discovered, currently in a scientific study phase with no confirmed launch date or funding. The mission concept targets a distance of 500 to 1,000 astronomical units within 50 years, 5 to 10 times farther than Voyager has traveled in nearly 5 decades. Achieving that range in that time frame requires a spacecraft traveling at roughly 80,000 to 160,000 miles per hour, approximately 2 to 4 times Voyager's speed. The proposed method involves a close solar flyby, using the sun's gravity combined with advanced propulsion to achieve the necessary velocity. Every instrument choice for the interstellar probe concept is informed directly by what Voyager found, and equally by what Voyager could not measure precisely enough, or could not measure at all. Breakthrough Starshot represents a more radical concept from private initiative. The project proposes accelerating gram-scale light-sail spacecraft to 20% of the speed of light using a ground-based laser array, sending them to Proxima Centauri on a 20-year journey at 20% of light speed. The atomic collision problem identified by Voyager's density measurements becomes acute. The energy deposited by interstellar hydrogen atoms on a gram-scale sail traveling at that velocity would erode materials at rates that challenge the limits of any known material science. Solutions are being researched. None are yet proven at the required scale. What Voyager established, more than anything else, is that leaving the solar system is physically possible with technology built by human hands, not future technology, not technology requiring theoretical breakthroughs. Technology designed with slide rules and built in the early 1970s. 2 spacecraft did it. They are doing it right now, at this moment, traveling through interstellar space and returning data that no theoretical model fully anticipated. And when looking back across the full arc of the journey from the launch pad at Cape Canaveral in 1977 to interstellar space in 2012, there is one single moment that captures everything the adventure means. One small photograph that changed the way humanity sees itself. On February 14, 1990, Voyager 1 was approximately 40 astronomical units from the Sun just beyond the orbital distance of Neptune, still decades away from the heliopause, still carrying functional cameras that had been scheduled for permanent shutdown. Carl Sagan had been arguing for years that before those cameras went dark forever, the spacecraft should turn around and take one last look at the solar system it had spent 13 years leaving behind. The proposal was not universally supported within NASA. Turning the spacecraft required using attitude control fuel that could not be replaced. The scientific value of the images was debatable. No new planetary science would result from photographing tiny dots of light at such enormous distance. But Sagan persisted, and eventually NASA agreed. On that February day, Voyager 1 rotated its camera platform and took 60 frames covering most of the solar system. In one of those frames, Earth appeared as a point of light smaller than a single pixel, caught in a scattered ray of sunlight that had entered the camera optics at a slight angle, pale blue, barely distinguishable from the camera noise surrounding it, indistinguishable from any random bright speck in the image if you did not already know exactly where to look. Sagan looked at that image and wrote what became one of the most widely read passages in the history of science writing. He described every human being who had ever lived, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher and student, every act of courage and cruelty, every moment of triumph and suffering in the entire recorded experience of the human species, all of it having occurred on that dot, a mote of dust suspended in a sunbeam. His point was not despair, it was perspective. The scale of our conflicts, our certainties, our sense of cosmic importance, all of it measured against that image and found to be something other than what we had assumed. When Voyager 1 crossed the heliopause in August of 2012 at 121 astronomical units, Earth was 6 times farther away than it had been when the pale blue dot photograph was taken. At 121 astronomical units, the entire angular diameter of Earth's orbit around the Sun was smaller than the resolution limit of any camera Voyager carried. The planet was not merely a tiny dot. It was invisible, not too faint to photograph well, but genuinely undetectable below the threshold of any instrument on the spacecraft. From interstellar space, Earth does not appear in the data at all. From that vantage point, the entire solar system, 8 planets, hundreds of moons, the asteroid belt, the Kuiper belt with its billions of objects, the theoretical expanse of the Oort cloud, all of it compresses into a region of space centered on a single star that is itself one of approximately 400 billion stars in the Milky Way galaxy. The Sun from interstellar space is a point of light. bright enough to be among the more prominent stars visible in that region of sky. But a point nonetheless, indistinguishable in kind from the hundreds of billions of other points of light surrounding it in every direction. The discoveries Voyager made at the edge of that solar system leave three questions that science cannot currently answer with certainty, and perhaps never will answer completely. The first, if the heliosphere, the cosmic home that surrounds and shields every living thing on Earth, turned out to be larger, more asymmetric, more dynamic, and more structurally complex than the best scientific models of the 20th century predicted. Then what else about our immediate cosmic environment are we currently misunderstanding in ways we cannot yet recognize? The models were built by brilliant people using sound physics and the best available data. They were wrong in almost every quantitative detail. That is not an indictment of science. It is a demonstration of science's fundamental character. But it raises an unavoidable question about what the next generation of models, the ones that seem most solid and well confirmed today, will look like after the next generation of spacecraft goes somewhere new and measures something directly for the first time. The second, if the interstellar medium immediately outside our heliosphere differs from models in density, temperature, magnetic field orientation, and dynamic behavior, then how accurately do our models of the broader galaxy, the structure of spiral arms, the behavior of interstellar clouds, the propagation of cosmic rays across thousands of light years reflect the reality that instruments inside those structures would actually measure? We have no Voyager for the broader galaxy. We have observations from Earth and from spacecraft that have never left the inner solar system. Everything we know about the galaxy beyond our immediate stellar neighborhood is inferred from signals traveling across distances that dwarf the distance Voyager has covered in nearly 5 decades of travel. The third question is the one that cannot be answered within any human lifetime or any foreseeable scientific program. If the golden record attached to each Voyager spacecraft is found, after billions of years of travel, by some intelligence that evolved on a world orbiting some star in some galaxy, what will they understand about us? Will the mathematics be decipherable? Will the pulsar map still function as a locator after millions of years of pulsar timing changes? Will the concept of music translate across whatever sensory apparatus that intelligence possesses? Will they understand that the heartbeat encoded on that disk belonged to a living creature that was frightened and curious and temporary? And will anything of human civilization remain at the moment of that discovery? Or will the record be the only evidence that we ever existed at all? Voyager does not answer these questions. It raises them with a clarity and an immediacy that no abstract philosophical discussion could match. Because Voyager is not a thought experiment, it is a physical object, built by human hands, carrying human sounds and human images, drifting through the space between the stars at this moment while you are reading these words. Every answer it returned from the edge of the solar system created new questions larger than itself. Every boundary it crossed revealed another boundary farther out. Every model it tested required revision. That is not failure. That is exactly what exploration is supposed to do. And as those two spacecraft continue drifting through the darkness of interstellar space, the question is not where they will go. The question is what we will do with everything they taught us. Two small spacecraft, built from aluminum and titanium, powered by decaying radioactive heat, guided by computers weaker than a wristwatch, crossed the boundary of the solar wind and entered a region no model had ever described correctly. Every number they sent back told the same story. The boundary was in the wrong place. The shape was wrong. The magnetic field surprised us. The interstellar medium differed from every estimate, and the sun's storms sent waves beyond its own border into space we thought it could no longer touch. We did not understand our own cosmic neighborhood as well as we believed. We still don't. But that is not a reason for discouragement. That is precisely the reason to keep going. The universe is not a problem with a solution waiting to be confirmed. It is a question that rewrites itself every time we dare to move closer. The darkness beyond the heliopause is not a warning. It is an invitation. Voyager went first. proved the crossing was possible. It proved the other side is stranger and richer than anyone imagined. The question now is not what Voyager found. The question is who goes next.